Okay. Can we prove everything? Can we prove everything? Okay. Short answer, no. Okay. Now, from a convenience perspective, we're not going to prove everything you learned in high school. We're just going to assume that. But also from a mathematical perspective, we cannot prove everything. So there are things that we take for granted, truths that are self-evident that we believe, and then we work from those to prove other things. Okay. Those self-evident truths we call axioms. So axioms are self-evident. And I'll put self-evident in quotes because, we just claim they're self-evident. Self-evident truths we take to be true without proof. Okay, and now I'm going to give you an example of an axiom. Okay, and it's so fundamental, I think it's worth highlighting. So consider a set. A set of positive numbers. Okay. So 3, 7, 9, 5, 13. Okay, this is a set of 5 numbers. And I say, what's the minimum? So the minimum of this set is equal to 3. Now consider another set. 7, 9, 5, 13, 3, 19, ... Okay. So immediately the first thing you say is ... I don't know how to fill in the blanks. I don't care. I don't need you to fill in the blanks. Okay. I'm going to allow any positive numbers to come later. Okay. And this set could be infinite also. Okay, and I can say, what's the minimum? And, okay, we don't know. Okay, and why don't we know? Because you have to tell us what's this ... However, I can make some deductions from here because look, I see the number 3. So either the minimum is 1, 2, or 3, as long as all the numbers in this set are positive numbers, are natural numbers. Okay. If 1 or 2 appears later, then it's not going to be 3. If you don't get 1 or 2 appearing later, then the minimum is 3. Okay, so we don't know the minimum, but as long as this set of numbers contains only natural numbers, we sort of believe that the minimum is either 1, 2, or 3. In other words, the minimum exists. Okay. Inside the set, the minimum exists. Okay, and it's a member of the set. Okay, so this is a non-empty set. Empty set of n. So a non-empty subset of n. And as long as you have any non-empty subset of n, we will assert that the minimum exists inside this set. We just may not know what that minimum is. Okay, so axiom. Okay, so axiom. And this axiom is called the well-ordering principle. Any. Okay. So this and this are examples because it applies to any non-empty subset of n has a minimum. Okay. So here it's clear it's 3, and here we don't know what it is, but somewhere in this set will occur the minimum. We just don't know what it is. Okay. We can get an upper bound. It's either 3, 2, or 1. Okay. But we don't exactly know what that minimum is. But it exists inside the set. And no matter what the set, okay, as long as the only thing in the set are natural numbers. Now, to show you that, this is a non-trivial axiom, let me give you another set of positive numbers, okay, and we will ask if this property holds. Okay, so here's another set of positive numbers, which is the set, R, where R equals 1 over k for any k in the natural numbers. So for any natural number, I'm going to take the reciprocal. So what is this set? This is the set 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on. So you might think, oh, any set must have a minimum in the set. No, look at this set. What's the minimum? Okay, now unlike here where we could say the minimum is at most 3, it's either 1, 2, or 3. Here, well, what do we think the minimum is? Could it be 1 over 1,000? No, because 1 over 1,001 is in the set, so that's not the minimum. In fact, any number in this set that you choose will never be the minimum, because there's always a smaller number. Because look, this set is infinite. In fact, if we were to try to build some definition of a minimum for sets like this, which we typically would call the infimum, okay, we would say that, the only reasonable minimum for this set is 0. Okay, because that's the only that's the largest number we can think of, such that everything in here is at least 0. Okay, but the problem is 0 is not in that set. Okay, whereas here we're claiming that whatever the minimum is going to be in that set. Okay, and that's very important. Okay, not every set of positive numbers has this property. It's a very special property of the natural numbers. And now that I've presented it to you, think about it and see how non-trivial this property is. You might even try to think, can I prove this property? And it turns out, no, we cannot prove it. Okay, we have to assume this property. It's called the well-ordering principle. Okay, now I want to show you a more sophisticated proof, one that uses an axiom, in particular this axiom. Okay. And this is a gift that came to us from Hippasus, and we must be very grateful to him because he gave us this gift. Okay. Okay, and what was this gift? So the gift from Hippasus. Okay, so Hippasus, was around in the Pythagorean times, in the Pythagorean school of mathematics, and according to the Pythagoreans, everything that can be measured can be represented as a ratio of numbers. In other words, everything that can be measured is a rational. Okay, so imagine this conversation that could have taken place between Hippasus and Pythagoras, a giant. Okay, it was basically Pythagoras who claimed that everything that can be measured is representable as a ratio of numbers, as a rational. Okay, so Hippasus comes to Pythagoras and says, Pythagoras, I got this field. Okay, and it's 1 kilometer by 1 kilometer. I'm going to split this field to give my friend half of it. So I'm going to split it along this diagonal. My friend is going to get half of this. Okay, but I'm going to charge him for the fence. Okay. And in order to charge him for the fence, I need to know what this length is. So Pythagoras looks at Hippasus and says, come on, man, I invented a theorem for this. It's even called Pythagoras' theorem. This length is the square root of 2. Okay, then Hippasus says to Pythagoras, but whoa, Pythagoras, you said that any length that I can measure should be representable as a ratio of numbers. So you need to give me this length as a ratio of numbers. That's what I need. I don't want this fancy thing that you call square root of 2. Okay, so Pythagoras says, come on, Hippasus. I don't waste my time. I already gave you this great theorem that told you what this is. Now go and figure out what this ratio is. So Hippasus goes off, tries to figure out what's this square root of 2 as a ratio of two numbers. Tries hard, fails. And so then Hippasus thinks, well, maybe it's not. So he comes back to Pythagoras and says, Pythagoras, I don't think this can be represented as a ratio of numbers. And Pythagoras goes, what? Blink, 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 wink, 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 blink, what? No way, I don't believe you. Come on. This is, you're going against the Pythagorean school. If you're going to make such a wild, rash statement, you better be prepared to prove it to me. Okay. So this is how Hippasus proves it to Pythagoras. Pythagoras, square root of 2 is not equal to a over b, is not a rational. So this is Hippasus. Okay, and Pythagoras says, you better prove this to me. I think you're full of you know what. Okay, and so Hippasus says, so Pythagoras, you don't think this is true? Pythagoras says, of course it's not true. It's fundamental. Everything can be represented as a ratio. So therefore, Pythagoras, you are saying that the square root of 2 is equal to a over b. Pythagoras says yes. And we all know from algebra that, you know, once you have a fraction, you have many ways to represent that fraction. For example, if you have 1 over 4, that's the same as 2 over 8, that's the same as 3 over 12, and so on. So once you have a fraction, there are many ways to do it. So if you can do it in one way, then you can do the square root of 2 in many ways. Let's call it a1 over b1, a2 over b2, and so on. a3 over b3. Okay, there are many ways to do it. Okay, so Pythagoras says, yes, of course, come on, basic stuff. Okay, don't waste time telling me this basic stuff. After all, I am the inventor of the Pythagorean theorem. Okay. And then, but now here comes Hippasus' deadly blow. He says, but Pythagoras, look, these denominators, remember the denominators in the rationals, we said they must be natural numbers. Okay, so these denominators are a subset of the natural numbers. Yes, of course. So if they're a subset of the natural numbers, and it's clearly a non-empty subset because there's at least one way to do it, then there must be a minimum, because that's the well-ordering principle. So here we're invoking that beast, the well-ordering principle. So Pythagoras says, yes, there must be a minimum. So let's call that minimum b star. Okay, and corresponding to b star, whatever it is, there's the corresponding a star. And it must be the case that a star over b star is equal to the square root of 2. Yes, of course. Okay, so a star over b star is the square root of 2, and Pythagoras agrees. And now this is where Hippasus really enters and shows Pythagoras that it's not Hippasus himself who's full of, you know what I mean, it's Pythagoras who's full of, you know what I mean. Okay, so Hippasus goes as follows. Well, if b star is the minimum possible, it means that a star and b star have no common factors bigger than 2. I mean bigger than 1. And Pythagoras says, yeah, obvious, because if they had a common factor bigger than 1, you could divide it out and get a smaller b star. Okay, so I'm going to box this, Pythagoras, because you agree with it. Okay, so what this means is that a star is equal to the square root of 2 times b star, which means that a star is equal to 2b star squared, because a star squared is equal to 2b star squared. I squared both sides. Pythagoras says yes, yes, yes. Okay, but what this means is that a star is even. Pythagoras says yes, obvious, because a star squared is even because it's a multiple of 2. But then we proved, Pythagoras, that if a square is even, it came from an even number. So this means a star itself is even. Yes, yes, good, good. Okay, good. So what this means is that a star is equal to 2k. Yeah. Okay, but now let's plug that in, Pythagoras. So 2k squared is equal to 2b star squared, which means that 4k squared is equal to 2b star squared, which means that 2k squared is equal to b star squared. Yeah. Okay, so, but Pythagoras, this means that b star squared is twice some other number. So b star squared is even. Yes, b star squared is even. Okay, but we proved that, you know, if something is even, we might not know what b star is, but we know that this means b star is even. Yes, Pythagoras, I mean Hippasus, you're wasting my time. Yes, b star is even. So then Hippasus comes down and says, okay, so we have found out that a star is even and b star is even. And b star is even. And now Pythagoras starts realizing that he's gotten himself trapped. He gave in to all these obvious steps, but he had no choice but to give in to these obvious steps. Okay? And now he has ended up at a spot where he, being the giant that he is, has realized he has fixed himself. Because if A star is even and B star is even, they have a common factor which is 2. But he already conceded they have no common factor. Okay. And now Pythagoras is going crazy in his mind and he's saying, wow, whoa. I'm the one who's full of, you know what? This is not possible. How can I allow you to produce this kind of nonsense that they have no common factor and then they have a common factor that is 2? The only way is that, my forcing you to abandon this claim and adopt this claim must be wrong. So this must be wrong. Okay. It means that this must be right. But what does that say? It says that the square root of 2 is not irrational. And that's the end of the proof. And it's a very weird proof. This convoluted argument where you start by giving away the whole game and conceding to Pythagoras that maybe Pythagoras is right. Pythagoras, you're right. Square root of 2 is irrational. But then look, you end up in all kinds of nonsense. Okay? And because you end up in all kinds of nonsense, you couldn't have been right. It was me who was right. This kind of argument is called a reduction to absurdity. Okay, and we'll talk about it later. This is a kind of argument that we typically use in mathematics where you string together known theorems and facts in order to get to where you want to go. Okay? So we use the fact that we use the well-ordering principle that any set of natural numbers has a minimum. Any subset of natural numbers has a minimum. That's where we got this and this fact that A star and B star have no common factor. We used standard algebra. Okay, we use the fact about even squares coming from even numbers. And this is an example where, we don't know what A star is. We just know that it must be even.